Hi everyone, so let's review this example that we did in class. Find the eigenvalues and eigenfunctions for the boundary value problem. We have this DE here and we're given these two initial conditions. So the first thing we do is always we find the characteristic equation. So the characteristic equation is r squared plus lambda is equal to 0. So if we consider the solutions of this characteristic equation, we're going to get r is equal to plus or minus the square root of negative lambda. And we have three cases. We have two real and distinct roots if lambda is less than 0. We have repeated roots if lambda is equal to 0, and we have complex roots, pure imaginary if lambda is greater than 0. So we have these three cases and we have to consider them one by one. So let's start with the first one. So I'm gonna erase this and start with the first one. So let's consider the first case, which is that mu is less than 0, and we're gonna define a new constant, mu squared is equal to negative lambda. We're gonna do this just for convenience because when we're writing down our solutions, we don't want a bunch of square root signs. So we're just going to define this for convenience. Our ODE is now going to become y double prime minus mu squared y is equal to 0 because of this minus sign here. And if we write down our characteristic equation, we're going to have r squared minus mu squared is equal to 0. So r is going to be plus or minus mu. And if we write down our general solution for this, so our general solution is y is equal to k1 e to the mu x plus k2 e to the negative mu x. Is basically doing the same thing that we did when we had real roots for our solutions. We just write the linear combination of the exponential functions. We take the positive root here and the negative root here. But we can realize that if we realize that sinh of x is equal to e to the x minus e to the negative x over 2, and cosh of x is e to the x plus e to the negative x over 2, we realize that this C1 and C2 are linear combinations of these two things. So we can easily write our solution more conveniently as y of x is equal to C1 cosh of mu x plus C2 sinh of mu x. So this is the solution that we're gonna use because it's more convenient when we apply our boundary conditions, you know. And the reason why we do this conversion is because it's more convenient. But I just want to emphasize that the sinh and the cosh just comes from the fact that this is just e to the x over 2 minus e to the negative x over 2, and this is just e to the x over 2 plus e to the negative x over 2. So basically it's just a linear combination. Here it's a half, here it's negative a half, here it's a half, here it's a half. So we could write our general solution like this. Or we could write it we could write it separately, like y1 is equal to cosh of mu x, and y2 is equal to sinh of mu x, like whatever is more convenient. So let's use our general solution, plug in our initial conditions to see if we have eigenvalues and eigenvectors when lambda is less than 0. So now that we have our general solution when lambda is less than 0, so I'm going to write it down here again. Y of x is equal to c1 cosh of mu x plus c2 sinh of mu x. And I'm going to write down these properties here in the side just to remind us when we're solving when we're putting our boundary conditions, is just going to help us. So just recall that cosh of 0 is equal to 1, and that sinh of 0 is equal to 0. We're going to need this because we have 0. We're going to need this because we have zeros here. So cosh of 0 is equal to 1, and sinh of 0 is equal to 0. Alright, so let's plug this in. So our right boundary condition, our left boundary condition is that y of 0 is equal to 0. So if we plug in 0 here, we're going to get y of 0 is c1 cosh of 0 plus c2 sinh of 0. So we know that sinh of 0 is equal to 0, and we know that cosh of 0 is equal to 1. So we can get that c1 is equal to 0, because 1 times c1 is equal to 0, so c1 is equal to 0. But what about our right boundary condition? So our right boundary condition is that y of 1 is equal to 0. If we plug in y is equal to 1, we're going to have c1 cosh of 1 plus c2 sinh of 1 is equal to 0. Alright? And since we know that c1 is equal to 0, we know that this term vanishes. And actually, it's going to be sinh of mu, because it's sinh of mu times 1, right? When we get to this part, it really helps to consider the graph of sinh of x to write this down. So, first of all, the graph of sinh of x is something like this. So, x sinh of x. We know that sinh of x is equal to 0 at 0, x equals 0, but it's not 0 anywhere else. So if we consider this, since we know that it's not 0, we know that mu is greater than 0 because lambda is less than 0. We know that this term here cannot be 0. So since sinh of mu cannot be 0, then we know that c2 has to be 0. So when we know that c1 and c2 is 0, we know that our solution is the trivial solution, because we're going to have y of x. All these terms are going to vanish, c1 and c2, so we're going to have y of x equals 0. This is the trivial solution. And for finding eigenvalues and eigenfunctions, we don't want the trivial solutions. So when we have c1 is equal to c2 is equal to 0, we can say that there's no eigenvalues for lambda less than 0. no eigenvalues for lambda less than 0. So this is our conclusion for our first case. We still need two more cases to consider. Two more cases to consider. So let's consider the second one now. So let's consider our second case, that lambda is equal to 0. So if lambda is equal to 0, the ODE becomes, y double prime is equal to 0, because this term is going to be 0. And what solutions do we have from this? Well, if we write down our characteristic equation, we're going to get that r squared is equal to 0, so r is equal to 0 and 0. So we have two repeated roots. So basically, our solution, our general solution, is going to be y of x is equal to c1x plus c2. Because we see that if we plug in 0, it's basically we're saying that c1x e to the 0 plus c2 e to the 0. So these terms are equal to 1. That's why we have the solution of this form, just to be a little bit clearer. So this is our solution. When r is equal to 0 and 0, we have two repeated solutions. And then we use our boundary conditions to see if we have any eigenvalues and eigenfunctions. So our left boundary condition is that y of 0 is equal to 0. So y of 0 is equal to c1 times 0 plus c2 is equal to 0. And from here, we can tell that c2 is equal to 0. c2 is equal to 0. Now let's talk about our right boundary condition. Our right boundary condition, we have that y of 1 is equal to 0. Therefore, when we plug in 1 in here, y of 1 is equal to c1 plus c2 is equal to 0. And since we know that c2 is equal to 0, this term vanishes and we're left with c1 is equal to 0. Here again we have c1 is equal to c2 is equal to 0. So since c1 equals c2 is equal to 0, since c1 is equal to c2 is equal to 0, there are no eigenvalues for lambda is equal to 0. And that is because our solution, our general solution would be the trivial solution. Y of x is equal to 0. So since our constants are equal to 0, there are no eigenvalues for lambda equals 0. But let's consider our third and final case, that lambda is greater than 0. And let's see what we find. So in this case, we're also going to define lambda in terms of something else. But in this case, instead of writing mu squared is negative lambda, we're just going to say mu squared is equal to lambda. And then we're going to see how that simplifies our calculations later on. So when we define mu squared is equal to lambda, our ODE becomes y double prime plus lambda squared y is equal to 0. So our characteristic equation is r squared plus mu squared is equal to 0. So solving for r, we're going to have plus or minus mu I, where I is the imaginary number. So r equal plus or minus mu I. So our general solution is going to be y of x is equal to c1 cosine of mu of x plus c2 sine of mu of x. And this is just what we've learned before. When we have complex roots, we just do the linear combination of cosine and sine, because since our real part is going to be 0, so our general solution in full would be this: c1 e to the lambda t cosine of mu x plus c2 e to the lambda t sine of mu x. And where this lambda here, it's not this lambda. I don't want to confuse you guys, but I'm just explaining, like going over the process of how we find the general solution. This lambda means the real part of this solution, which is 0. We just have the imaginary part. So this is 0, which means that e to the power of 0 is equal to 1. So we're just left with this part. I hope I didn't confuse you. I just wanted to explain why the e to the power of lambda t is not there. But yeah, so this is our solution, and that is all that matters in this case. And let's use our boundary conditions to see what are the eigenvalues and eigenfunctions. So if we say that, so let's do our left boundary condition. Our left boundary condition, y of 0 is equal to 0. 0 is equal to 0. We're going to get c1 cosine of 0 plus c2 sine of 0 is equal to 0. Since sine of 0 is equal to 0, this term here vanishes, and since cosine of 0 is equal to 1, we know that c1 is equal to 0. So now we're left with our final way of finding the eigenvalues and eigenfunctions, so we know that this one will have to work. Let's consider our right boundary condition. Our right boundary condition, we have that y of 1 is equal to 0. So if we plug in y is equal to 1, we're going to get c1 cosine of mu plus c2 sine of mu is equal to 0. Since we know c1 is equal to 0, this term here vanishes, and we're left with this expression: c2 sine of mu is equal to 0. Alright, so since we want, we want to find the values that c2 does not equal to 0. So for us to have that, we need that sine of mu is equal to 0. So do you understand that? In order to preserve this equality, that c2 times sine of mu is equal to 0, we want we want c2 not to be 0 for us to not have a trivial solution. So we need that this part of the equation is equal to 0. So this should not be equal to 0. So we'll say that sine of mu is equal to 0. If sine of mu is equal to 0, what do we have? For what values of mu is sine of mu is equal to 0? Well, we say that mu is going to be equal to, I don't know, 0, pi, 2 pi, 3 pi. We kind of see the pattern, right? So a number like an integer times pi. So we could write down as mu of n is equal to n pi, where n is an integer. So our eigenvalues is this. So I'm going to erase this part of the board so I could write down our eigenvalues and eigenfunctions in this side of the board. So just erasing this part. So this is what we have. I'm going to write the things that we need here. So our general solution, which I erased, but I need to write it back again, is y of x is equal to c1 cosine mu x plus c2 sine of mu x. I hope that fits there. So this is our general solution, and we found our values of mu. Mu is equal to n pi, where n is an integer. So our eigenvalues, lambda is equal to mu of n squared, which is equal to n pi squared. And our eigenfunctions, we're just going to plug in our values of mu here. So our eigenfunctions y of n is just going to be equal to, first of all, it's just going to be equal to this right here. But since we concluded that c1 is equal to 0 on the last part, like I erased this over here, but we showed that c1 is equal to 0, so this term vanishes. So our solution is just going to be c2 times sine of mu, not mu squared, so mu n pi x. So this is our eigenfunction, and we don't need the c2 right here, so if you want, you could just write it mu of n is equal to sine of n pi x. So this is how we solve this problem in class. I'm just bringing it up to review it again. Might be helpful, and I'm going to be doing more exercises like this that wasn't in the homework for additional practice. So this is how we find the eigenvalue, this is how we find the eigenfunction. I'll see you guys next time.